Hi everyone, welcome to the Meet the Speaker video. I'm Yang, and here I'd like to introduce our paper, Shape-Based Conditional Neural Field for Waistworn Change Point Detection. This research comes from a story between me and my supervisor, Professor Oi. Last year, I went to his office and talked with him about my master's thesis. And during the talking, my phone kept popping up the notifications of many apps like Facebook, Instagram, and this is actually annoying. So during that time, I'm thinking that can I design an algorithm that can make my phone smarter so it won't pop up the notifications when I'm working. So the scenario is like this. First, I collect the time series data from my watch, like iWatch, and then I can use the algorithm to detect the transitions between these activities. And once it detects the activity and the transition, it can tell my phone that now you can pop up the notification. So this is the beginning of the research, and this is also the reason why we want to design the algorithm for change point detection. And as for change point detection, so what is change point detection exactly? Change point detection is the problem of identifying abrupt changes in time series data when the underlying physical process changes by analyzing only the observed time series data and without knowing the underlying process. We found that we can divide the existing SOTA into two categories. First is the unsupervised and supervised learning methods, and then the non-deep learning and deep learning methods. We found that all these SOTA cannot work well for human activity change point detection on the wrist-worn devices because of two challenges. The first challenge is that the limited computational ability of wrist-worn devices requires that the algorithm run on the wrist-worn devices should be efficient and also effective. And we can find that from the table 1, the computational time for inference per segment in the extrasensory dataset. We can find that the RIF and KLCPD performed very bad. And the segment length is about 0.2 seconds, and we can find that ROSIF and KLCPD spent almost 5 seconds to predict 0.2 second length segments. And although we can say that LSTM is not bad, it performs fast, but the performance, the AUC, is one of the worst. And the second challenge is the human activity is a highly complex process that can generate many varying patterns. We extract two segments from the extrasensory dataset. We can find that the first figure shows the subject is standing and moving while studying, and the second figure shows that the subject is standing and moving while driving. Although they have the same main activity, standing and moving, the patterns of these figures are very different because they have different secondary activities or the concurrent activities. So the existing algorithm cannot tell this difference and cannot detect the change point very smoothly in this human activity data. So it is to this end that we propose our method ShapeSynF, which is an online, simple, and fast change point detection algorithm that works well on human activity data collected in the wild. And ShapeSynF is designed to achieve three goals. First, it should learn the underlying change patterns, and then it should adapt to the dynamics and complexity of the data generation process. And the most important is it should be simple and efficient enough so that it can be deployed on the WristSense devices.